Welcome to another paper reading session. Today I am explaining a paper titled Masked Autoencoder for Distribution Estimation by Matthew Germain, Carol Greger, Ian Murray, and Hugo Lerchel. The paper was published in 2015 and has more than 350 citations. This is a very important paper as the findings of this research as well as the proposals are used as a component in many other density estimation algorithms. So think of this paper as the building block for other algorithms. I have organized this tutorial into 3 sections. In the first section, I will describe the goals of this paper, that is the problems that they are trying to solve along with the associated challenges. I will also provide the essential background knowledge that is being relied on to produce the solution to the problems. Then I will describe the key insights delivered by this paper and the big idea or the central idea of this paper. And finally, in the third section, I will show you the experiments they conducted using their proposed method and the results. So let's start with the goals and the background first. As such, the very high level goal can be understood from the title of the paper itself. That is, they are trying to devise a technique to do distribution estimation. Here I have used an alternative word called density estimation just so that you know that these two words can be used interchangeably. Now, density estimation techniques are generally classified into 2 categories, non-parametric methods and parametric methods. This paper has invented a new parametric method. And when we say parametric method, it means that you first assume or figure out by some other technique what is the type of your distribution, and then you are going to do the estimation of its parameters. So for example, maybe the distribution that you selected for your random variable is a normal distribution. So the next task is to figure out mu and sigma for your probability distribution. While I have made it simple by stating that first select a distribution and then find its parameters, it's not at all this simple. In many ways, density estimation is harder than many other machine learning problems. And one of the reasons it is challenging is because most of the real world data sets are high dimensional. You see, quite many times for mathematical and computational convenience, we assume independence amongst the samples of our data set as well as independence between the components of a multidimensional sample. So this paper will address challenges like this, that is density estimation for high dimensional data. The title is so well crafted that it also reveals the technique they are proposing for distribution estimation. There are 2 words to note here. First is autoencoder and the second is masked. The autoencoder is a well-known neural network architecture. So they are essentially proposing a modification to it and calling it a masked autoencoder. We will discover what masked means in the insights section. So first let's see why they plan to use the autoencoder. Here is an example of autoencoder architecture. I have color coded the various neurons. Yellow means the inputs, green is for hidden layers, and this last layer looks a bit different as it has a circle inside it. This type of a neuron is called match input output neuron, that is, it should output the value that is same as that of input. Basically what you have in the yellow neurons. Since there are 4 neurons, each sample is a 4-dimensional vector. I am showing one example of such an input here. Please don't be confused with the notation. Here x1, x2, x3 and x4 are the components of a sample and are not independent data samples. Here I am showing the components of this sample associated with each input neuron of our autoencoder. On the output side, I am showing x1 hat, x2 hat, x3 hat and x4 hat. As I said earlier, the output layer of the autoencoder is supposed to recreate the inputs to the network, but we will not necessarily will get the exact same values, and hence I have put a hat on the symbols to indicate that. We can write our output vector as x hat Since it is a neural network, you also need a loss function so that you can learn the parameters of various layers. And it is very easy to imagine, at least in this case, a canonical loss function would be a mean squared loss. That is, just compute the difference between the x hats and the inputs, square them, and average the loss of all the samples of your mini batch. The last part in this diagram that I want to bring your attention to is the hidden layer. As you can see that this hidden layer has a small number of neurons than other hidden layers. The outputs of this layer gives us what we call the latent representation of our input vector. Now the word latent has many meanings depending on the context. In this context, it is used to represent a lower dimensional version of your input. That is a 2-dimensional latent representation for a 4-dimensional input vector. But what do we get out of this? What is the use of latent representation? There are multiple use cases, but for now, one simple use case is that this latent representation has coded the most important attributes of your input vector. And thanks to this extraction of important aspects of your input, it makes the comparison between two input vectors better from the accuracy point of view. And not only accuracy, but it is suitable for computation as well, because now you're dealing with the lower dimensional vectors. I don't want you to get anchored by the fact that here I have used a 4-dimensional input and I have a 2-dimensional latent representation, and 2 is half of 4, but there is nothing like that. I could have chosen 3 neurons for my latent representation. Similarly, the input could have been even a bigger vector, maybe a 784 dimensional vector for my input. So for example, if you take MNIST image, which is 28 by 28, and then if you flatten it up, you will get 784 as the number of the pixels in it, and hence you will have a vector of 784. So there is no relationship here between 4-dimensional and 2-dimensional. It's a choice that you make when you are building your network. That all being said, what if I make the latent representation same size as that of an input? I mention this because maybe computational aspect is not an issue for the task at hand, and you may think that having more dimensions in this layer, that is more neurons in this layer, would increase the learning capacity. And there is a truth to that. You should think in this direction. But what may not be clearly visible from this architecture right now, from this layout right now, is that since the goal is to recreate your inputs, your hidden layers may just end up learning an identity function, because all they then would learn is how to simply propagate your inputs to your outputs, which means that you would very quickly end up getting a loss of 0 and you would consider your job done. But really, you would not have learned any good representation in the middle, the latent representation here, which is one of the primary goals of autoencoder. This is the reason you are recreating your inputs, because you want to learn some meaningful representation that happens in the middle of the network. So by reducing the dimension of one of the hidden layers, which we call our latent representation, we have forced the network to learn something meaningful, as it has to recreate the inputs from this low dimensional vector. It's like putting a little pressure on the network or constraining it. But is this the only way we can do it? Is this the only way we can force or twist the arms of our network? Not necessarily. Here I am showing you a variant of an autoencoder where the latent representation is of same dimension as the input vector, but the input neurons do look a bit different. You can see that I have a triangle symbol inside the yellow neurons now, and this indicates that the inputs are noisy. Well, the real world inputs are anyway noisy, but here in this case we are explicitly going to add the noise, and hence a specific symbol to indicate that. So it's a part of your data preparation, that is adding a noise. The goal of the autoencoder remains the same, that is to recreate the inputs but with no noise. And this is another way of constraining our autoencoders so that it can learn meaningful representation. So this type of an autoencoder is called denoising autoencoder. I hope you can start to see a theme here, which is that of constraining the autoencoder to learn what we want it to learn. And these observations led the authors of this paper to wonder if they could use the autoencoder to learn the probability distribution of the components of our input vector. But what does it mean to learn the probability distribution of components? Let me explain. The first version of this thought of learning the probability distribution may look something like this. Pay attention to this part of the network that has been modified. So here, instead of x1 hat, x2 hat, x3 hat, x4 hat, first I have replaced those with p of x1, p of x2, p of x3 and p of x4 respectively. And note that the color for the output neuron is also different now. It is green, not red. And this green neuron also has a circle inside it, and it represents what we call a probability neuron. I must admit that the first time you see a notation like this, it could be confusing. For example, by using p of x1, am I saying that the neuron is outputting the probability of x1, or it is outputting the parameters of a distribution p? And then maybe we use the parameters to compute the probability of x1. Let me make it clear with the help of a visualization. So assuming that your x1 is following normal distribution, you should think that this probability neuron is outputting two real values, a mu and a sigma. So it is not outputting a probability, it is predicting the mu and sigma for your probability distribution function. And then you use them to compute the probability of x1. This being clarified, we should also be able to express the joint probability of a sample like this. That is, the probability of each component is now a factor in joint probability of your sample. But then what should be our loss function to learn the weights? Well, the canonical way of doing parametric density estimation is to maximize log likelihood or minimize the negative log likelihood. You are essentially learning to predict the parameters of your distribution that would give the highest possible probability for your observed data. In simple words, you would compute negative log px for your mini batch. And for a 4-dimensional example, it would look like this. If you are not familiar with the usage of negative log likelihood as a loss function, but have written neural networks for classification, then this may be a bit confusing at first. So let me try to explain. So when you do image classification, you minimize the cross entropy loss between the ground truth label and the predicted labels. And then you stop your training when you have achieved a desired level of accuracy. So you are doing an image classification on dogs, and if it says, the network says that I'm 98% sure that this dog belongs to this breed, you're happy, you stop your training and you go home. But when do you stop? In this context, when do you stop when you have the negative log likelihood as the loss function? And the answer to that is not that simple, because you do not necessarily have a direct metric which tells you that you have now achieved a 98 or a 99% accuracy. So what you do is that you simply aim to minimize the log likelihood as much as you can, and there will come a time when it would not go lower. And maybe it is then you will stop your training. Another approach that you can do is that after every epoch, maybe you would want to sample from the distribution that you have now learned, meaning px1, px2, px3, px4. And then you essentially sample from this learned distribution and check if the sample that you are getting out matches somewhat your real data or not. And this would be one way for you to validate if your network has learned something useful. Now that the loss aspect is taken care of, the next part we should worry about is the strong assumption that I made here when I wrote the joint probability. The way it is factorized here indicates that there is no dependence amongst the dimensions of our input vector, and which, as I said earlier, is not representative of a real world situation. So if I were to incorporate conditional dependence, one way I can do it is to apply the chain rule of probability, which means that the distributions to which our output neurons will feed into would be conditional distributions. But there is still a problem here. The problem is, why should I believe that joint probability factorizes this way? So for now I have used what is called a natural ordering. I had x1, x2, x3, x4, and that's how I applied the chain rule. But what if it is the other way around? You see, the choice of order of components in the input vector is arbitrary. Let me explain this with the help of an example, and hopefully it will be clear that way. Let's say that you have a data set for houses and there are 4 fields, which means that it is a 4-dimensional data set. The fields are number of rooms, number of toilets, number of floors, and the distance from the city center. You can see and appreciate that these individual fields may depend on each other and hence have correlation. Now, to feed these to my neural network, I would put them in a vector form, and hence they could correspond to my x1, x2, x3, and x4. But then I chose this order at random. What if the order that I picked was this one? This means that my joint probability could look something like this as well. And therefore the corresponding joint distribution will be different, as well as the output node will have a different conditional distribution. In nutshell, the order is kind of important, but since we are doing density estimation, we just don't know what is the order. Well, we may always have some analysis and incorporate that when ordering the components of our vector. But in a setting of pure unsupervised learning, we may just want to throw the data at the network and let it figure out the most optimal relationship between our components. And the last observation that authors made is still associated with the conditional dependence aspect, but is regarding the connectivity between the various neurons and the layers in this figure. If the output neuron 1 in this example is supposed to be the distribution for x1 conditioned only on x2, shouldn't we make connections that respect this? That means we should not have connections to neuron 1 that came from x3 and x4. But as you can see in this figure, this is not the case here. Every output neuron seems to be connected to every input neuron. This brings us to the end of this section, and we are ready to state the goal of this paper. The goal should be simple to understand now, is to constrain the autoencoder to learn a joint probability distribution with conditional dependence. And it also needs to do it in such a way that it is agnostic to the ordering of the dimensions of a input vector. With that said, let's look at the key insights that are shared by this paper and the approaches the authors took to produce the solutions to the problems that we have discussed so far. The key insight or the big idea here is not that difficult to understand. Since we need to constrain the autoencoder, we can first and foremost drop the connections that violates the autoregressive property. Now, do not confuse autoregressive and autoencoder. They do share the word auto, but they are used in different contexts. What they mean by autoregressive property is that if x1 depends on x2, then it should not be seeing the inputs x3 and x4. Now, one way you could terminate the connections or logically drop the connections is to simply multiply the weights with a zero vector. Keyword here being logically. And Selection of which connections to keep and which ones to drop is done with the help of masks. Here I am showing you the figure from the paper that expresses this sentiment amongst many other things that it is showing. This figure was too crowded for my taste, so let me explain the algorithm step by step with the help of an animation while still using the same network architecture as that of this figure. Here I have drawn the network which is identical to the one from paper. In the previous section, I had used an autoencoder that took 4-dimensional input and had different number of hidden layers. But here I have replicated the one from the paper. Let me put them side by side so you can check. The only difference is that they have drawn it from bottom to top and mine is left to right. I like my neural networks to go from left to right. This is a little preference of mine. The network is your traditional autoencoder where the goal is to simply recreate the inputs, and hence you see the red output neurons with a circle symbol in them. We have seen this earlier as well. But a more interesting one is the one from the right hand side of that figure that I showed you earlier, and I have replicated that as well. And here you can see that I have the probability neurons in the output layer, and I'm showing you the picture from the paper as well. Now I will show you how to establish the connections between the neurons, and to do so I am first removing all the connections. As you can see in the picture from the paper, not all neurons are connected to each other. But to help you learn the algorithm, I'm going to explain it using an animation and simple steps. Let me make some room here. So the first step in the algorithm is to randomly assign a number to your input neurons. Here I have assigned 3, 1, 2. But why? Remember that in the previous section, I described that we do not know the order of the components of our input vector. The authors in this section are suggesting that for every mini batch, we will select a different order to work around this issue. They refer a paper from 2014 by Uria et al. That had already demonstrated this notion in the context of other autoregressive models. Now, what is important to pay attention here is that the output neurons should be assigned the same order. What about the neurons for the hidden layer? Same strategy again, more or less, that is generate a random vector. The little caveat is that the order will range from 1 to d minus 1, where the d is the dimension of your input vector. This means that the range for this example will be from 1 to 2 since we have d equals to 3. The reason is that for autoregressive property to hold true, we can only accept connections from the neurons that are assigned a lower number. Since 3 is the highest number possible, it will not be connected to any neuron anyways. So let's see it by connecting the neurons of our output layer first. The first neuron, the first one from the top in this screen is labeled as 3, the highest number possible in our scenario, which means that it can accept connections from all the neurons labeled lower than 3. Something like this. This is represented using equation 9 from the paper. As should be clear, it is saying that the mask value would be 1 if the label of the neuron is larger than that of our incoming neuron. Now the next neuron in our output layer is labeled 1, which is the lowest possible label anyway, so we should not expect any connection to come from the hidden layer for it. Finally, the last neuron in our output layer is labeled 2, and the only neuron which has a lower label than the 2 is 1, so we can make those connections, as should be clear. Let me now show you how to connect input neurons to the first hidden layer. Or maybe put differently, which connections the first hidden layer should accept. Since I'm showing you both ways to think about it, let's see it from the point of input layer this time. The last neuron in our input layer is labeled 2. So it should be able to make a connection to neurons higher than that. Now, this is where there is a difference between the policy that we saw in the output layer given by equation 9. So there is another equation in the paper which is equation 8, and this equation 8 applies to all the layers except the output layer. And this equation is stating that for all the layers except the output layer, you should be able to connect to neurons which are higher than you or labeled higher than you or has the same label as you. So in this case, this is the reason why we are able to connect the neuron label 2 of our input layer to the neurons label 2 in the first hidden layer. Now we can do the same thing for neuron labeled 1, but this time around it also has a neuron which is labeled bit higher than the 1, which is 2, so we are able to do that as well. Now the last neuron in our input layer, which is labeled 3, cannot be connected because this is the highest number that is there in our scenario. And for the rest of the hidden layers, it follows the same principle of equation 8. Let me show you the picture again, and if you tilt your head 90 degrees, you should be able to see that my illustration has the same connections as the one shown in this figure. Okay, fine, do not strain your neck, please. I'm going to show the illustration next. Here is my illustration showing the network from bottom to up direction. I really don't like my networks going from bottom to the top. Let me summarize the key insights. First, to respect the autoregressive property for conditional distributions, we need to mask some connections by logically deleting them. Second, since we do not know which component of our input vector depends on which other components, we sample an order before each mini batch. This gives the network an opportunity to explore all possibilities. The trick of sampling the order can be used during test time as well. That is when doing the prediction on the new input vector. You could create a few different orderings of the component of your new input vector and run the forward pass for each one of them. So let's say that you came up with 5 different orders, meaning 5 different forward passes, and then you just simply average the results of these forward passes. This is equivalent to having an ensemble of models, but the difference here is that you used the same network instead of having multiple networks. And finally, they also noticed that that sampling the order for each example was making the network difficult to learn or difficult to converge. There was too much variation for the network to handle, and as a remedy, they then generated a list of masks and recycled them. So this can be seen as a balancing act. Selection of the list of masks would then become a hyperparameter that you would have to figure out for your task at hand. Let's quickly look at the experiments and the results as well. So they use 2 types of data sets. The first one is the UCI data set, which itself consists of 8 smaller data sets. You can see the number of training and validation examples that they have available. Here are shown the results and their comparison to other models that came before them for density estimation. And many of these density estimation algorithms also make use of neural networks in one form or another. And as should be clear from this table, they are doing better for some data sets, but not necessarily for all of them. But quite frankly, there is no need to pay attention to these numbers anymore, as these are now very old results anyways. And the thing to really celebrate here with respect to MAID is the performance that they managed to get during the prediction time by their clever use of autoencoders. Especially if you do the comparison to another model called NAID, which by the way is also designed by the same authors, the performances are much better. So as it is shown in this little cutout from the paper, in NAID, if you have D dimensions, it would mean that you would need D forward passes, unlike one pass for MAID. I think this is pretty good. On top of that, the biggest win is that all the computations can now be vectorized by this smart usage of masks that they have come up. Here I'm showing you the results on another dataset they conducted their experiments on. The dataset here is a binarized MNIST. What they're showing you here is that they validated if the network was learning something useful by sampling from the learned distribution. As the figure on the left shows that they managed to recreate MNIST from the samples of their learned probability distribution. The interesting aspect of experiment for me was that they tried different number of masks to show how the negative log likelihood decreases with the increase in the number of masks. And we are at the end of this paper reading. I have already mentioned the key advantages of MAID, but one more time doesn't hurt, so it is highlighted here as well. This is a very well written paper, and the methods they propose are elegant and quite simple to implement. For this, I give the paper 5 stars. A job well done by the authors of this paper. As I mentioned earlier, MAID is now getting used in other algorithms such as autoregressive normalizing flows. I know that there is an implementation of MAID in TensorFlow probability library. There are multiple open source implementations for PyTorch as well. You just go to Papers with Code and you would find a list of all the repositories on GitHub that have the implementation. And with that, I now end this little paper reading session. I hope you learned something useful today. I sure did. It is possible that I was not clear with some aspects of this paper. So if you have queries and doubts, please do ask your questions in the comments and I would try my best to answer them. With that, thank you again. Bye bye.